Hello calculus students, this is graphical derivatives, where you learn the ability to take the graph of a function and sketch the graph of its derivative. It's also known as the red-green show, as you'll see in a second. Now, the red part of the show is for change. Red is the color of change, like revolution and sacrifice. And for a differentiable function, the change in f of x will tell you the sign of f prime of x, the sign of the derivative. So change in f of x. So when it's increasing, I'm going to use that INC to abbreviate that, or an upward arrow like that. When the function's increasing, the tangent lines will be increasing. And so the slopes of the tangent lines will be positive, so the derivative is positive. So that's what I mean by change in f of x leads to the sign in the derivative. If the function's decreasing, and sometimes I'll use this code, DEC, or just put a down arrow like this, the derivative is negative. And when a function's a constant or a relative max or min, a horizontal line is a constant, its derivative is 0. And the same thing you'll see when you reach relative max or min. Let's look at this in the graph of this parabola, x minus 1 times x minus 3. Now, we can see that on the left side of the parabola, the function is decreasing. As you go from left to right, it's going down, so the derivative will be negative. On the right, the parabola is increasing, so the derivative will be positive. And right here, we've got a relative min, and so the derivative is 0. And so we can just connect those up. That would be a quick sketch. Now, I also use some insight that, well, it looks like a parabola. I know the derivative of parabola is a line. And we can see it more precisely here. You can get better estimates of the actual value of the derivative by drawing some tangent lines and using rise over run. But the point of this exercise, the red-green show, is to just get the sense of the direction the derivative is going in, whether it's positive or negative, and whether it's increasing or decreasing. And we get that from hints we see in the original function. Now the green part of the show has to do with the concavity. Green is the color of concavity, like the green rolling hills that you read about in The Great Gatsby. Okay? For a differentiable function, the concavity in f of x will tell you the change of f prime of x. So, if it's concave up, sometimes abbreviate that CU, or put a little happy face like this. If it's concave up, that means that if I look at tangent lines, they're going to be changing. The slopes will be changing. How are they changing? In an increasing direction. If the original function's concave up, the derivative will be increasing. If the function's concave down, sad like that, the derivative will be decreasing. And if the function's neither concave up nor concave down, that means it's either linear, in which case the derivative is constant, or you've got an inflection point, IP, in which case you reach a relative max or min on the derivative. And let's see how that works here in our next example. We've got a cubic function drawn, and we can see, let's just do the green part of the show for right now, then we can talk about the red part. The function's concave down, it's sad. See the sad little frog there? And that's concave up. See how happy it is over here? Happy. So it goes from decreasing to increasing. And somewhere in here, the derivative must change concavity. And we call this the inflection point. It's sad beforehand, it's happy afterwards. So the original function has a change in concavity, it's got an inflection point, and that's either going to be a relative max or min. Well, if we were decreasing then increasing, it must be a relative min. And it looks like it's something negative, because we're clearly sliding down here. So I'm going to put a relative min down here. Now, to get more, so I get the sense we're going to get a parabola here, which makes sense if you start with a cubic. To get more, let's do the red part of the show. And that is, it's increasing, and then it's decreasing, and then it's increasing. And where it changes from increasing to decreasing, here's a relative max on the original function. And that relative max corresponds to a 0 on the derivative. Same thing with this relative min. It's neither decreasing nor increasing. It's changing from decreasing to increasing. So we plot that as a 0. This gives us a few more points to connect everything up with. When it's increasing, the function's positive. The derivative is positive. When the original function is decreasing, the derivative is negative. And when the function is increasing, the derivative is positive. So it all seems to be coming together here like this. We want to decrease, then increase. We want to go from positive to 0 to negative to 0 to positive. All seems to come together with a graph like that. So our sketch is not too far off of the reality there. All right. Now some other things to look for when you're doing a derivative. Vertical asymptotes or vertical tangent lines will lead to vertical asymptotes in the derivative. A horizontal asymptote means that the original function is getting closer and closer to being horizontal, and the slope of a horizontal line is 0. So you end up getting a horizontal asymptote at f prime of x equals 0. And a sharp corner, sometimes indicated like this, sharp corner, means that you have a change in slope. So you get a discontinuity in the derivative. The derivative is undefined right there. So vertical asymptote leads to vertical asymptote. Horizontal asymptote leads to a horizontal asymptote at 0. And a sharp corner means your derivative is undefined and you get a non-removable discontinuity, a sudden change in slope. So you're probably going to have to represent that as, like in this case, we got a sharp corner there. We have positive slopes, and then we have negative slopes. So you usually indicate that with 2 open circles to indicate that the derivative is undefined. Now, here's an example of what I like to call the bird function. It's x to the 2/3 power. Well, let's do the red part of the show first. It's decreasing, so we're going to be negative. It's increasing, so we're going to be positive. Now, what happens right here? It's not really, it's a minimum, but I can't tell if that's a sharp corner or not. Let's look at our concavity. This is concave down on the left. That means it's going to be decreasing. And it's concave down here on the right too, so it's going to be decreasing. So we don't get an inflection point here, but it looks like something's going on, like you get really steep slopes. And if we could zoom in, you'd see it on your, you can try it on your graphing calculator. You end up getting a vertical asymptote there, or a vertical tangent line. And remember what we said about vertical tangent lines, those lead to vertical asymptotes down here. So our derivative, I suspect, is going to go something like this. That's going to be decreasing and negative here, and decreasing and positive with this vertical asymptote in between. Now, an alternate interpretation of this, because let's say we didn't know this. We didn't know the exact equation. If I just looked at that, I might just label it as a sharp corner. So my decreasing section, negative, increasing section, positive, and I can see the concavity change. This is concave down and this is concave down. So we're going to be decreasing both times. And I might look at this and go, oh, that looks like a slope of about maybe over 1, up 4, or something like that. So maybe I put a slope of 4 just before that, and a slope of negative 4 after it. And so I connect up my graph this way, which looks a little different than the graph I have over here. But because it's just a sketch, and I'm not actually giving you the derivative here, the actual original function, if I just gave you the picture, I would accept an interpretation in either respect. Now, as it turns out, it actually does have vertical asymptotes there, because you got 1 plus x to the 2/3. And the derivative is going to be 0 plus 2/3 x to the negative 1/3. So you've got 2 over 3 cube root of x. And since that's the case, x cannot equal 0, and you get a vertical asymptote right there. Let's see what happens on a rational function. So first of all, the red part of the show, we've got increasing here, so we're going to expect positives right here. Then it's decreasing for this whole section here, so it's going to go negative. And it's decreasing again, so it's going to stay negative. Let's get our vertical asymptotes in here. Vertical asymptotes are a nice way to divide up the graph. this vertical asymptote here is just going to continue right along on the derivative. And the vertical asymptote I see in here continues on the derivative. Okay? Now we can look at the green part of the show, the concavity. This is concave up in here, so we're going to be increasing. This changes, and somewhere in here we suspect an inflection point. This is concave up, but then it becomes concave down. So we're going to increase and then decrease on the derivative. Here this is concave up again, so we're going to be increasing. And it looks like we've got a horizontal asymptote here as well. Let's get our horizontal asymptote in there. At y equals 2, roughly. So that means we get a horizontal asymptote at 0 on the derivative. Let me just fix that one. Yeah, that looks like a horizontal asymptote now. Okay, so how do we sketch this all in? Well, here goes the derivative. We are positive and increasing a horizontal asymptote there. Increasing then decreasing. Notice it's decreasing the whole time here, so we're going to stay negative. So use our vertical asymptotes. And the vertical asymptote here, but going up like this. Increasing and negative. Approach horizontal asymptote 0. Notice that this vertical asymptote, the function approaches, both of them approach positive infinity, but then it flips here on the derivative. And we see that over here too with the original function goes to opposite infinities on this vertical asymptote, and that means on the derivative it's going to go to the same infinity. And we see that happening, sure enough. Okay? Now actually the function might have dipped a little below here and started coming back up again, in which case that's a real subtle thing that maybe we can detect with the actual formula. I just had the sketch, that's what I would do. Technically, this derivative looks like it comes down, hits 0, and then starts coming back up again. Okay. Now, notice a few functions back that we had this bird function here. And you see how this bird function in black is definitely even. And the derivative ends up being odd. This is something you can count on. If you see that y-axis symmetry on the original function, then the derivative will have odd symmetry, and vice versa as well. So that's why I add those to the little chart at the end here. If f is even, then the derivative is odd. If the original function is odd, the derivative is even. If the original function is undefined or it has a discontinuity, then you can't have a derivative. The derivative is also going to be undefined. Okay? All right. Flange.